Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. All right, TWiML listeners, this is your last chance to register for my upcoming AI Summit. The event takes place next week, April 30th and May 1st in Las Vegas, Nevada, in conjunction with the Interop ITX conference. I'll be presenting an introductory session on ML and AI fundamentals, and we'll have deep dive sessions on AI for NLP and conversational applications, computer vision, and Internet of Things. Then we'll be discussing more strategic topics, including data collection and annotation, operationalizing and managing AI, and building out your organization's AI culture and strategy. Attendees will also have a chance to discuss their organization's unique AI opportunities and challenges with our panel of distinguished experts. To learn more about the event, head on over to twimlai.com/AI Summit for details and a discount code. In this episode, I'm joined by Marco Cuturi, professor of statistics at Université Paris-Saclay. Marco and I spent some time discussing his work on optimal transport theory at NIPS last year. In our discussion, Marco explains optimal transport, which provides a way for us to compare probability measures. We look at ways optimal transport can be used across machine learning applications, including graphical, NLP, and image examples. We also touch on GANs, or generative adversarial networks, and some of the challenges they represent to the research community. And now, on to the show. All right, everyone. I am here in Long Beach, California at the NIPS conference, and I am with Marco Cuturi. Marco is a professor of statistics at Université Paris-Saclay. Université Paris-Saclay is how I should say it.
You perfectly fine.
Marco, welcome to the podcast.
Thanks for having me.
So why don't we get started by having you tell us a little bit about your background. Now, you're coming at things from a stats perspective, but applying them to the world of machine learning and AI. How did you combine these interests?
Yeah, exactly. So so here we're at NIPS, so I might maybe start with that. I've been coming at NIPS for about, I think, 12 years maybe, since I was PhD student.
And you haven't missed any?
No, I have missed a few in the middle, but let's say I've probably been here more often than not during those years.
Okay.
So probably maybe 7 times, something like that. And my background is, so as you mentioned, I have more of a mathematical training in statistics, maybe a little bit of CS. It's a blend of everything because I come from a French grande école, so those are universities that try to give you a pretty general training. And when I was a PhD student, I was interested in machine learning already.
Okay.
I was doing bioinformatics. Trying to do bioinformatics with some mathematical tools. And then I kept from there, and I did a bit of finance. I worked also in the financial industry for a short while, and worked as a lecturer in the US for a while as well.
You said an actor?
Sorry. As a lecturer.
Lecturer, okay.
Sorry, no, it's not as exotic. No, definitely more. So I was in Princeton for a while, and then I worked in Japan as well for a long time. I was a professor there for 6 years, and then just 1 year ago, actually, I came back to France.
Okay.
So I looped back to France, and yes, as you said, my training is more in maths, so I'm more interested in the, how can you say, well-behaved, well-posed problems, mathematical problems that we can think of, and try to apply them and make them work in actually the messy setting of the real data, etc.
Okay. And so one of those mathematical tools that you're working on now is called optimal transport. And in fact, you did a tutorial on that here at NIPS. What is optimal transport?
Yeah, so it's been a bit the main subject of research for me for about maybe 3-4 years now. Mm-hmm. Before that, I was so maybe if you see NIPS through the years, there's waves of technologies and ideas and methods that come by, and so one of them was kernel methods, and that was when I was a PhD student.
Okay.
And then it started receding when deep learning exploded.
Okay.
Boomed. And then I had an interest for this theory for a while. The theory dates back to the 18th century. It was developed by a French mathematician. It's very intuitive concepts, but for a while there was no real progress. And then this was rediscovered in the 20th century by a Russian mathematician called Kantorovich, and he got a Nobel Prize actually in the 70s in economics for work on this theory. And then more recently, there's also a very famous French mathematician. You might know him. He was recently elected, like in the French Congress, and he also got the Fields Medal, which is like the biggest prize you can get in mathematics. His name is Cédric Villani, and so this is a really beautiful theory that many mathematicians have been investigating for the last decades. And I think recently we made some progress on the numerical side, computational side, and this can become very relevant in machine learning. So across those 3-4 years, we've seen a wave of papers that have, I think, proved a bit that this was useful. And now the tutorial was a way to showcase a bit all that progress.
Okay. So for someone who's not familiar with optimal transport, what is it and what is it trying to achieve?
Yeah, so let's just break it down in 2 words, right? So
okay.
It's optimal and transport. So what do we mean by transport? Transport is actually, it really dates back to a very simple idea of transporting goods from where we produce them to where we need them.
Okay.
And typically, of course, if you only have, let's say, one mine and one factory, then there's not many questions you should ask. I mean, you just bring whatever the mine produces and you bring it to the factory to transform it into some other goods. But now suppose that you have a map and you have a lot of mines everywhere on the map, and they all produce this, raw resource in different quantities, and then you have factories all over the map as well, and they all need that resource for them to keep on producing final goods. And the question is how you move, those resources around in an optimal way, in a cheap way. So it's really related to a deep problem, in operations research or just industrial problem, which is optimally move things. And this was the reason why this really boomed as a theory in World War II, is that this is probably when really we had a bottleneck.
A lot of stuff to move.
We had a lot of stuff to move, and we really wanted to be optimal. It was not just a matter of profits or trying to squeeze more money or anything.
Right.
This was just vital.
Right.
You would have to, there were some, front lines, you would need 10,000 soldiers there, 20,000 soldiers there, etc. And then you had them in another place, another location, and you really had to find out very quickly what was the best way to do that. And so, unfortunately, during World War II, I guess none of those techniques actually were used, but that situation triggered a lot of thinking, and that's why Kantorovich and actually other people here in the US as well, Hitchcock, Koopmans, there's lots of names that are associated with this problem. And then this was really a topic that was mostly investigated by people in operations research. But then gradually, this idea of transporting things in an optimal way also found applications in, for instance, in physics. Like you would try to guess how a distribution of gas would slowly evolve towards another distribution of gas. There's many, many different settings where you're basically trying to compare those two things, like the probability distribution of what you have and the probability distribution of what you would like to get and how to transform it optimally. And so this is why mathematicians got interested in that. And from our point of view, basically it boils down to the following thing. This idea of optimal transport provides a fresh way to look at what we call probability distributions. So probability distribution is basically quantifying how things are likely to happen. They also quantify basically where we observe data. What kind of images do we observe in the real world, right? We don't observe just any kind of image, we observe images with a certain structure. And so those observations form a probability distribution, and we try to come up with probability distributions of the world, which we as modelers is what we can do, and we try to compare them, and this is where the theory is actually useful.
And so I'll stick with this background question. Is the implication then in the context of World War II, like they were probabilistically modeling troop movements as opposed to I would imagine that to be more deterministic.
So,
like I'm going to move these troops from A to B as opposed to.
You have a very good point. So here, let me just tell you, how you could imagine probabilistic troop movements. Imagine you have front line A and front line B, and you need 10,000 soldiers at A and B, okay? Because somewhat the enemy is coming, so you really need 10,000 guys there and 10,000 guys there. Suppose you have 2 barracks, each with 10,000 soldiers. So a very naive way would be to, let's say, send all the 10,000 soldiers of the barrack 1 to frontline A, 10,000 soldiers from barrack 2 to frontline B. Okay? So there's no real probabilistic thing, right? It's just everyone goes there and then everyone goes there. This sounds great. But imagine that, I don't know, for some reason you're a bit suspicious that maybe something might happen to the 10,000 soldiers that are sent through just one road. So one thing you might try to do is split those 10,000s into 5 and 5. And the other barrack also is split into 5 and 5. And so you send simultaneously 5,000 soldiers to each of the front lines. You see what I mean?
Yeah, so now you've got 4 routes.
Exactly. You have 4 people moving, 4 groups of people, 4 groups of 5,000 people moving around. So it's not clear you gain a lot by doing that, right? Because somewhat maybe if barrack 1 was very close to frontline A and barrack 2 was very close to frontline B, then you're actually asking people to cross basically over and have this much longer trip, right? But what you've gained is that you have something of maybe this is where maybe the probabilistic aspect can be seen. Like each soldier basically from barrack 1 had chance 1/2 to go to A or B. Or on the other hand, if you want to just stick to the optimal plan, you would just send them directly to the closest line, right?
Is what you're trying to model probabilistically the chance that they'd actually get there, like the danger of their route or some kind of...
This is something that you might have in mind to actually choose the one where they split into 2 instead of just going directly to the best possible, the shortest basically frontline point. But what I'm saying is that when you have to distribute resources in a network like this from a starting point to an ending point, well, sometimes you can find that the best possible way, cheapest possible way, is to do this a bit deterministically, as you implied. There's no probability; you just send everyone to the best possible route. But you could add some little fuzziness. So you know what? Maybe in case there's a problem with that route, maybe this breaks down, this bridge breaks down. If this bridge breaks down, maybe no one will get to frontline B, and then I'm really in a mess, right? So to hedge a bit yourself, you might want to choose something that's a bit more fuzzy, a bit more probabilistic.
Okay.
And on the other hand, if you really go towards the most, the fuzziest possible way to do this, where you split everyone equally, then you see that there's a problem because you're paying a very high cost usually in terms of travel. Right. Because maybe frontline B is like 100 miles away, frontline A is maybe 10 miles away from the barrack 1, and you're actually asking for the half of your troops to walk those 100 miles, right? So see, there's a trade-off somewhat in terms of robustness. On the one hand, you would like to do what's cheap. On the other hand, adding a little bit of fuzziness makes it a bit more robust against any problem that might occur. So here, I'm using this vocabulary of maybe there's a risk or there's something that might break down, etc. But from a mathematical perspective, what this really boils down to is more something which is the stability of the solution, basically. Having a little bit of fuzzier things makes it a bit more stable. Having something that's really routing everyone to just one location makes things a bit unstable. And so
makes me think of if you're familiar with Nassim Taleb's anti-fragility.
Yeah, exactly. You could think of this. So we're going a bit away from basically my exact technical contribution, but actually the idea is exactly that. Okay. And part of my talk. So first I explained this problem of moving around optimally things. This moving around optimally things helps you figure out whether 2 things are close, whether 2 distributions are close. If there's a cheap way to move all the troops to all the front lines, then it means that the 2 distributions are very close. Okay. That if you write down the equations, and this is why Kantorovich got the Nobel Prize, this yields something called a linear program.
Mm-hmm.
It's one major, very important family of optimization problems.
Mm-hmm.
And the way this was formalized 50 years ago was just linear programming. So let's go for the cheapest possible distribution. Now, what I was arguing a bit during the tutorial is that you might trade off a little bit of that optimality in terms of the cost and accept a little bit of fuzziness. And this makes things much better behave computationally when you run all those algorithms. So actually this...
Meaning that introducing the randomness not only has these properties, these beneficial properties in kind of the physical world, we're talking about troop movements, but also introducing probability and randomness allows you gives you a more computationally efficient solution than solving a linear program?
Yes. Like 1 million times faster.
Wow.
Like in some relevant dimensionalities, let's say you have, 10,000 barracks, 10,000 front lines, and you want to compute this optimal transport.
Right.
Well, it turns out that if you're willing to take a little bit of fuzziness, not that many, but just a little bit, then it can actually, you can compute this transport in maybe, let's say 1 second, for the sake of the argument. But if you were to solve it with a linear program, that would be like 1 million times slower. That would be really much longer. And the other thing that's also very relevant, I think, in this NIPS conference, is that computing transport with that little fuzziness, not so much, but just a little bit, allows you to compute everything on GPUs. So everything becomes a parallel, very embarrassingly parallel algorithm. And this is one of the also big sources of speed up. Whereas doing it the linear programming way, the way that was proposed in the 50s or 60s by such great names as George Danzig, people that invented all those algorithms in the 50s or 60s, those algorithms don't parallelize well on GPUs. And this is the main reason why we're trying to get a bit away from them and a bit more towards those algorithms that, because they include some fuzziness, a little bit of fuzziness, for some reason, if you go down in the math, you observe that you can cast them as matrix products, and so everything works well on GPU.
Interesting.
So if I want to push a bit the analogy, this field of optimal transport has been around for many years. I propose this little, to add this little fuzziness, and everything all of a sudden can be executed on GPUs. So it looks a bit like someone that comes at a machine learning conference maybe 10 years ago and says, oh, I have deep learning algorithms. Not only are they great, actually they run on GPUs. And because they run on GPUs, they are going to get much better performance.
Right.
Because, as we know, this was one of the main drivers of innovation for deep learning, was the fact that they could really well exploit GPUs. So that's...
So then, are you also applying optimal transport to machine learning problems?
Yes.
Or are you, is this a method for doing better work with traditional types of problems that we think of as optimal transport or transport problems?
So yeah, it's a very good question. So my point of view right now is that, so maybe I didn't stress this enough, but what really optimal transport allows you to do is to compute the distance between probability distributions. And by this I mean, let me just give you a very concrete example. And this was actually presented at NIPS last year by another team. So suppose you want to compare two text documents. So a very standard approach is to see those documents as bags of words, right? Just a long list of words and another long list of words. So I think it's a very relevant question to say, how can we compute the distance between those two bags of words, right? So there are a few approaches that exist. And one of them is using optimal transport. So basically what this optimal transport approach requires is that you're able to define a distance between pairs of words. So basically, if you can define a distance between pairs of words, optimal transport allows you to define a distance between histograms of words. It's like a meta distance. You have the distance on just, the word cat is that meters away or miles away from the word, let's say, dog, and then very close to kitty, for instance. If you can actually quantify that distance for every pair of words, I will be able to come up with a distance that can quantify the distance between histograms of words, clouds of words, point clouds, all those point clouds that see very often on
word clouds.
Word clouds. So the optimal transfer allows you to compute that very accurate distance between word clouds. And now, what I'm trying to use is, suppose that my goal is not only to compute the distance between two things, but also to use that distance as what is called a loss function.
Okay.
Something that allows you to quantify whether your prediction kind of matches what you should observe. So imagine, so this is another example I was taking for an IPS paper 2 years ago. Imagine that your task is to predict from an image a cloud of tags. Okay, so you just see an image, there's a tree, sun, bridge, etc. Imagine now that you have a predictor that takes that image and says that on that image actually it's a forest, there's sunlight, and there is a river. So as you can see, I've managed to find a few tags that are somewhat overlapping the original tags that are the ground truth. But it would be really useful if I could accurately quantify how different those two histograms of words are. And that's where optimal transport can be used. And so what I've shown in the tutorial yesterday is that you can not only use optimal transport as a distance just to put a geometry on the space of histograms, but you can use that as a loss in a learning algorithm. So whenever I will, so very often, for instance, an algorithm just produces one guess. Well, just think about a meta algorithm that would not produce one guess, but a histogram of guesses. So probability distribution, some confidence on basically several possible guesses. Well, then it's useful to use optimal transport theory to compare those histograms of guesses. Instead of, maybe you've heard about this, Kullback-Leibler divergence or other. There is a very important block in many machine learning algorithms, include deep learning algorithms, which is this cross-entropy loss or Kullback-Leibler loss. Well, this is another loss that has been around for centuries to compare to probability distributions. Basically, my main agenda is to maybe remove that loss and replace it by this optimal transport loss.
Okay. And what are the advantages in doing so? You mentioned the computational advantage with our ability to do these in parallel. Is that something that you can't do with cross-entropy loss?
No, actually, it's the other way around. Cross-entropy is very popular because it's very, very simple. It's very, very easy to compute. But it uses very little information. In the sense that, imagine that you have two histograms of words.
Right.
And I compute the cross-entropy between them, or the Kullback-Leibler divergence. What that won't be able to detect is whether words are synonyms or not. In the sense that if, for instance, one of my histograms, the one that I want to predict as the word cat, and for some reason my machine predicted the word kitty, in the cross-entropy world, those will be two completely different coordinates. And there's no...
relative.
There's no basically the cross entropy formula will just say, okay, cat appeared here in the ground truth. My guess was kitty, so I have put a 0 on cat. Then you pay a price. And then on the other hand, the ground truth didn't have the word kitty, but I predicted it, so you also pay the price. You pay the price twice if you want.
Right.
Whereas this optimal transport loss allows you to say, oh, come on, actually, the ground truth is cat, and my prediction is kitty, but I know that cat and kitty are very close. I mean, they're almost the same. They're almost synonyms. So I'm paying a very small price because I'm able to somewhat transport the word cat onto the word kitty. And that's the main idea why this gives a loss, which is more flexible, if you want.
Now, it sounds like in this case, it's calling to mind like word embeddings and word spaces.
Exactly.
And so do you need to do all that in order to use?
So the thing
is that an alternative? Or are they complementary?
No, so exactly. So basically, so in those papers, those people are called word movers distance, because the idea of optimal transport actually has many names. It's called Wasserstein distance, earth movers distance. And so it was recently discovered by this word movers distance, where you're actually computing the distance between 2 point clouds of word embeddings. So you can imagine that one text is just a bunch of points in dimension 100. Those are the embedding dimension of the words. And another point cloud is another text in dimension 100. And then you're trying to transport them optimally. And what you need to do to get there is a notion of distance between every pair of words. And so that's what the word embeddings gives us. So word embeddings are just the fuel for this. I mean, just the main ingredient that allows us to compute optimal transport.
Okay, interesting. So there's an application in NLP. What are some other machine learning applications?
So we have, so let me just list you what the application where things really work very, very well.
Okay.
So the ones where it works really nicely is graphics.
Okay.
So it's a bit away from machine learning because graphics people are mostly concerned with low dimensional shapes.
Mm-hmm.
So we've had a few successes, doing interpolations of shapes, and we have a few C-graph papers.
And what are the specific examples?
So one very specific. Well, imagine that you have a probability distribution, which is a shape, and another probability distribution that's a shape. What optimal transport allows you to do is to do interpolations between them, like morphing, with very, very little assumptions on the data. So what we've seen is that this can be used.
So can you give me a more kind of concrete example of where you'd have these probabilistic shapes?
Yeah, so it's one of those cases where a picture actually is worth 1,000 words, but we have those pictures in those C-graph papers where you would see, for instance, I don't know, a duck, like the kids have in the bath, that would gradually morph into some cow or any other shape.
Okay.
And then we can actually compute interpolations between tens of shapes. One another application in brain imaging, we can try to morph one brain into another without making any assumption on actually a parametric assumption on the shape of the brain, for instance.
And so optimal
transport is very natural for that.
Right. So you've got your beginning distribution, your end distribution, and now this allows you to compute intermediate states at any point
which are
in time or
geometrically
point in.
faithful, which makes sense geometrically, because it's very easy to compute intermediate probability distribution. You just add one to the other, divide by 2, but then you will probably get those weird effects. Because optimal transport actually allows you to morph continuously from one to the other. Okay. And this was discovered in the late 90s. For many years, we had no idea how to compute it because it was actually very, very heavy. And those ideas that I told you about adding a little bit of fuzziness, exploiting GPUs, basically make it possible now. And so you can average not only 2, but maybe, let's say, 10, 20 brains and things like that. So that can help you form templates. So those are the examples that are actually visually a bit more striking. It's low dimension. We as humans can get a feel of what's going on. Then the NLP applications, I think, are pretty exciting. And then there has been
the what applications?
The NLP applications that you mentioned. And then we had there's a lot of imaging also applications with distributions of colors, for instance, like image palettes, morphing one image with a given palette, changing the palette of an image, for instance. Like I don't know, the palette has colors reminiscent of autumn, and you want them to be all of a sudden kind of bluish, etc. So there's lots of applications like this. But what we've seen in machine learning recently, and which is pretty exciting, is more applications to generative models. Those models, that are able to create images. And so there's been a few papers in the last year, actually, in just 1 year from now. And one of them is called the Wasserstein GAN. It has attracted a lot of attention. We've also tried to write a few papers in that line. So here, in that case, the story is as follows. You can see the distribution of natural images in the world, let's say, as a probability distribution over the space of all possible images, right? So if you think of an image as 3 channels and 100 times 100 pixels, it's basically a vector of dimension 30,000. But there's very few, actually, in that space of dimension 30,000. There's not that many images that are natural in there, right? If you were to basically write a map of every image that can be natural, it would be very thin there, right? So the problem of generative model is to create a probabilistic model, something that can generate images that fall not too far from that manifold of natural images. Right? And this is a statistically very, very messy problem. And so what you want to do is, imagine that I have a model that generates images. It will have its own manifold in that space of dimension 30,000. And then I collect data. That's another manifold in dimension 30,000. And so the point is, I want my manifold to look like the manifold of natural images, right? And I need to be able to say how far I am, right? That's the whole point of doing gradient descent. It's quantifying how far my manifold is from the real manifold. and trying to make that distance smaller and smaller.
Right.
And what people found out in just about 1-2 years ago is that many usual distances like cross entropy, Kullback library, etc., were not well suited for that problem, because we're really talking about very degenerate manifolds. And what we use Kullback library for is typically to compare Gaussians, for instance, or to compare things that are very smooth.
Mm-hmm.
And so when you have this problem of trying to quantify the distance between one manifold and another, optimal transport can be useful.
Okay.
And so there's been a lot of interest for that. So this Wasserstein GAN has spurred a lot of papers. There's many tricks that people are trying to use to make this work, because it's computationally challenging. But then again, in the world of GANs, it's very difficult to measure performance. So right now everybody's a bit frustrated, but I think there's still a bit of progress that's being made now.
I haven't picked up on the frustration around GANs as much as the enthusiasm.
Well, if you talk to
frustration
people,
specifically around the ability to measure performance?
Yeah, exactly.
Okay.
Exactly. I mean, if you look at the papers, most of them end up being a collection of images that are being generated, and that's not a very scientifically correct way of you want some more objective measure of performance, but that in itself is already a big scientific problem, right?
Mm-hmm.
Trying to find a good measure of performance there.
Okay, interesting. I really enjoyed learning about optimal transport. Any final words or?
Oh yeah, so we've written a small. I'm just doing to put some little advertisement for a survey that we've written recently. So if you go to optimal transport and just one word, optimaltransport.github.io.
Okay.
You will find the slides of the tutorial, and you will find also a survey, a 200-page survey that I've written with my colleague Gabriel Perret.
Okay. Interesting. And is there, in terms of, you mentioned GitHub, and I'm thinking implementation. Is there code available?
Yes, of course. Yes,
okay.
There's code. Yeah.
Okay.
The good thing is that, as I was telling you earlier, all of this eventually is actually very simple to code. I mean, I wish I could tell you we have really a great toolbox that, but actually, if you really look a bit at the papers, it's just, the code is just a few lines. It's just to basically put that loss, this magic optimal transport loss in your learning problem, just requires you writing maybe a while loop and 3 lines in the while loop.
Okay. So it's more, that's right up your alley. It's more about the math that gave you those 3 lines.
Exactly.
And the
There's
3
not
lines
much engineering
themselves.
involved, yes.
Okay. Awesome. Well, Marco, thanks so much for taking the time to chat with me.
Thank you so much. It was really a pleasure.
All right, everyone. That's our show for today. For more information on Marco or any of the topics covered in this episode, head on over to twimlai.com/talk/131. And of course, thanks so much for listening, and catch you next time.